Lesson 1.4 focuses on more counting principles. Often we want to know how many possible ways an event can occur. We have 4 methods for determining the number of possible outcomes in a given situation. We've already looked at the first 2 methods in a previous lesson, the addition counting principle and the multiplication principle of counting. We use the addition counting principle when we have a single action experiment. With the multiplication principle of counting, we use that when we have a multi-action experiment. In this section, we're going to look at 2 more. We're going to look at permutations and combinations. Before we move on to permutations and combinations, we have to look at the math concept of factorials. The definition of a factorial, n factorial, and I just use the letter n to represent any number, and the exclamation point is read as the factorial. That's our symbol for factorial. Well, to evaluate n factorial, I take the number, I multiply it by 1 less, I multiply that by 1 less, I multiply that by 1 less, and I continue on until I get down to 3, 2, and 1. This is easier to show with an example, so let's look at our first example, 5 factorial. I begin with 5, and I count down until I get to a 1, and I multiply these numbers. So 5 factorial is 5 times 4 times 3 times 2 times 1. And if I multiply these, I get 120. In the next example, 7 factorial, I start with 7 and count down until you get to 1. So we're going to have 7 times 6 times 5 times 4 times 3 times 2 times 1. If I multiply these, I get 5,040. I want to show you how to use the factorial button on your calculator. So take out your TI-30XA, and the factorial button is a second function over the number 3. So if you look at the yellow lettering right above the 3, it's x factorial. So if I wanted to enter 5 factorial, I'm going to type a 5, and then to get to the second feature, I hit my second button. And then you'll see the little notification at the top that you did activate the second feature. And then I press a 3. And that gives me my 120. If I want to do 7 factorial, clear out your screen, type the number first, 7, and then hit second, and then the number 3 for your factorial. So you get 5,040. Now let's look at some special factorials. Let's begin with 1 factorial. Anytime you have 1 factorial, that just equals 1. Remember, with a factorial, you start with the number in front of the factorial symbol and you count down until you get to a 1. Well, when you have 1 factorial, there's nothing to count down. You're already at the 1. So 1 factorial will always be 1. Next, let's look at 2 factorial. 2 factorial is always 2 times 1, and that's always just a 2. Then finally, 0 factorial. By definition, 0 factorial is always 1. This is one you just need to memorize. And a special note, if I have 8 factorial divided by 4 factorial, I cannot reduce the 8 and the 4. I can't divide the 8 by 4 and get 2 factorial. Let's look at why. First, if I expand the 8 factorial and the 4 factorial, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Well, I can reduce this by canceling the 4's and then the 3's and the 2's and the 1's. After I expand it, I can reduce these when I have no factorial symbols present. So that leaves me with 8 times 7 times 6 times 5, which is 1,680. And if you remember, if I had divided the 8 by the 4 and got 2 factorial is just a 2. So that would definitely not equal the 1,680. Another way I could expand this, you can stop a factorial expansion at any point by inserting the factorial symbol. So when I expand the 8 factorial, I can write it as 8 times 7 times 6 times 5, and then at the 4, I can put the factorial symbol after the 4. Now the 4 factorial in the numerator will cancel with the 4 factorial in the denominator. So I still get the 8 times 7 times 6 times 5, which is 1,680. So just remember, you can only cancel factorials if they are exactly the same. You cannot reduce factorials. You can't simplify them like you would a fraction. You can only cancel the factorials if they're exactly the same. So now let's move on to permutations. A permutation is a subset of elements in which order is important. That's what you need to remember about permutations. You use a permutation when order matters, when the order of the events is important. The notation for permutation is a capital P followed by what looks like an ordered pair. And there's going to be 2 numbers in that ordered pair. The first one is an N, which is the total number of objects. The second is an R, which is the number of objects we're selecting. So this notation represents the number of permutations of N objects taken R at a time. Another notation for permutation is to use the capital P, and in front of it you use a subscript N, and following it you use a subscript R. So in that second notation, the N and the R are subscripts. And books commonly use both notations. The formula for a permutation is N factorial divided by N minus R factorial. So you take the total number of objects and use its factorial in the numerator. Then you subtract the 2 numbers, the total minus the number that you're selecting, and take the factorial of that difference. And as we mentioned before, N is the total number of objects, and R is the number of objects that we're using or that we're selecting. So let's look at an example. This is a permutation of 8 objects, choose 3. So my N is an 8 and my R is a 3. So I have 8 factorial over 8 minus 3 factorial. Well, if I subtract the denominator, I end up with 8 factorial over 5 factorial. To do this by hand, I'm going to expand the 8 until I get to the 5. So I'm going to write 8 as 8 times 7 times 6 times 5 factorial. Now that 5 factorial will cancel with the 5 factorial in the denominator, and I'm just left with 8 times 7 times 6, which is 336. In the next example, I have the permutation of 6 objects selecting 2 at a time. So my N is a 6 and my R is a 2. So by definition, I have 6 factorial over 6 minus 2 factorial. If I subtract the denominator, I get 6 factorial over 4 factorial. Well, I'm going to expand the 6 factorial until I get to a 4. So I'm going to write 6 factorial as 6 times 5 times 4, and then stop it there by using the factorial symbol. Now the 4 factorial in the numerator will cancel with the 1 in the denominator, so I'm left with 6 times 5, which is 30. Now I want to look at how to do these on the calculator. On the calculator, your permutation button is above the 9. It's the second feature. It's the NPR. So what you're always going to do is type in the N first. So in the first example, we had the permutation of 8 objects, choose 3. So I'm going to type the 8, and then I'm going to hit second and my 9 for the permutation, and then I type a 3 and hit equals. And that gave me my 336. My second example was 6, choose 2. So I'm going to type in the 6, hit second, and then the 9 for my permutation, and then type a 2 and hit equals. And that gave me my 30. So you type in the first number N, hit second, and then number 9 for your permutation, type in the second number R, and then press equals. Now let's look at some examples of word problems using permutations. How many possible codes does a combination lock have if each code has 3 digits, no 2 numbers of the code are the same, and the lock dial has 100 notches? So in this case, I have a 3-digit code. And when you have a code, order is important. If the combination code to your lock is 123 and you enter in 321, the lock will not open. So the order of the digits in the code does matter. Since order matters, this is a permutation. I have 100 possible numbers to choose from, so my N is 100. Of those 100 numbers, I'm choosing 3. So I have a permutation of 100, choose 3. Now you can either work this out by hand using the formula, or you can work it out on your calculator. Either way is fine. If we do this on our calculator, we have 100, and then I hit second, number 9 to get to the permutation, and then the 3 numbers that I'm selecting, and press equals. And you get 970,200. So there are 970,200 different possible codes. In the next example, how many different ways can a baseball coach arrange a batting order of 9 players if there are 15 players on the team? With a baseball lineup, order matters. If the batters bat out of order, it's an automatic out. So if you put batter number 1 first and batter number 2 second, they have to appear in that order. If you switch the 2 batters, that's a different lineup. Since order matters, this is a permutation. I have 19 total players to choose from, and I'm selecting 9 to go in the lineup. So it's a permutation of 15, choose 9. On the calculator, I'm going to type a 15, hit second, my 9 for permutation, and then press 9 again because I'm selecting the 9 players, and hit equals. So I end up with 1,816,214,400 different lineups. In the next example, how many ways can the letters of the word math be arranged? Well, I'm taking the letters from the word, so each letter is only being used one time. There are 4 letters total, and I'm using all 4 letters. The order matters. If I write this as M-A-T-H, that's one arrangement. If I write it as A-M-T-H, switching the A and the M, that's a completely different arrangement. So changing the order matters, so it's a permutation. And as we mentioned, we have 4 letters in the word math, and we're using all 4 letters. On our calculator, I'm going to type 4, hit second number 9 to activate the permutation, and type a 4 again. So I end up with 24. So the letters can be arranged 24 different ways. In the next example, how many ways can the letters of the word mom be arranged? First, let's just look at the different arrangements since there's only 3 letters. I have M-O-M. If I switch the first M and the O, I have O-M-M. And then if I switch the last M and the O, I have M-M-O. If I switch the 2 M's, I'm still going to have M-O-M. The word's going to look the same. So just by playing around with this, I see that there's 3 possible arrangements. Now the order matters, so this would be a permutation. So let's look at a permutation of 3 choose 3. If I type the 3 choose 3 in my calculator, I have 3, hit second and 9, type your 3 again, and hit equals. This gives me 6. The problem is when I work this problem out on paper, I know that switching the M's gives me the same word, so I don't count that as a different possible arrangement. When you use your calculator doesn't know what the letters were, so it considers each of the M's as different letters. So we have to have a way to work around this. The rule is when you have repeats, when you have repeated letters or repeated objects, you must divide by the factorial of the number of times a number or an object is repeated. So in this example, I had 2 M's. So I have to divide by the factorial of that 2. If the M had been repeated 3 times, I would have divided by 3 factorial. If the M had been repeated 5 times, I would have divided by 5 factorial. That's taking out the example of where I just switched the M's and end up with the same word. So we saw that the permutation of 3 choose 3 was 6, and I know 2 factorial is 2, and when I divide the 6 by 2, I do get the 3, and that's the same as the 3 arrangements we found above. So look at the next example. How many different ways can the letters of the word Mississippi be arranged? Well, Mississippi has several repeated letters. So I take each letter one at a time. The M occurred once, the I occurred 4 times, the S occurred 4 times, and the P occurred twice. So I have 11 total letters, and I'm using all 11. So it's a permutation of 11 choose 11. But this time I have to divide by the factorial of the number of repeated objects. So there's several repeated letters. So I have to divide by 4 factorial for the 4 I's. I have to divide by another 4 factorial for the 4 S's. And then I have to divide by 2 factorial for the 2 P's. So I suggest you simplify the numerator in your calculator and then simplify the denominator and then go back and divide them. Don't try to enter this in all in one step. Let's look at this on our calculator. Begin with the permutation of 11 choose 11. So I have 11, hit your second and then the 9. and then type in another 11 and hit equals. So this gives me 39,916,800. That goes in the numerator of your fraction. Clear that out and let's evaluate the denominator. So I had a 4 factorial, so hit 4 second, and remember your factorial was above the 3. Times, I had another 4 factorial, so hit 4 second and the 3 again. And then times, if you remember 2 factorial is just a 2, so I'm going to type a 2. And I get 1,152. That goes in the denominator of your fraction. So now that I have the numerator and the denominator of the fraction, I divide those. And I end up with 34,650. So the letters in the word Mississippi can be arranged 34,650 different ways. Next, let's look at combinations. A combination is a subset of elements in which order is not important. That's how you distinguish between permutations and combinations. In permutations, order is important. In combinations, order is not important. So the notation C and then the parenthesis with an N, R inside of it represents the number of combinations of N objects taken R at a time. There are 2 other notations for combinations. Like permutations, I could have a capital C with a subscript N in front of it and a subscript R behind it. The final notation for a combination is an N over an R, and it looks like a fraction without the fraction bar, and that's enclosed in a parenthesis. So just 2 little notes. When you have the subscripts, the N and the R are subscripts. They're written smaller than the C. And then if you use the third notation, it looks like a fraction, but there's not a fraction bar between the N and the R. Don't draw a fraction bar in there. The formula for a combination, N choose R, is N factorial divided by R factorial times N minus R factorial. So it's the same formula as permutations, but I have an extra R factorial in the denominator. And again, the N is the total number of objects, and R is the number of objects used or selected. They're the same variables used in permutations. Let's look at an example. This time we have the combination of 8 choose 3. So my N is an 8 and my R is a 3. So I have 8 factorial over 3 factorial times 8 minus 3 factorial. If I subtract the 8 minus 3, I have 8 factorial over 3 factorial times 5 factorial. I'm going to expand the 8 until I get to a 5. So I'm going to write 8 as 8 times 7 times 6 times 5 factorial. That 5 factorial will cancel with the 5 factorial in the denominator. Now in the denominator I also took the 3 factorial and I expanded it. And if you notice, I just wrote 3 times 2. Technically I should have expanded that until I get to a 1. But multiplying by 1 doesn't change, so if you want to leave off the 1, you can. So my 5 factorials will cancel, so I have 8 times 7 times 6, and then the 3 times 2 on the bottom, I went ahead and multiplied those to get a 6. My 6's will cancel, leaving me with 8 times 7, which is 56. In the next example, let's look at the combination of 6 choose 2. So my N is a 6 and my R is a 2. So I have 6 factorial divided by 2 factorial times 6 minus 2 factorial. The 6 minus 2 gives me a 4, so I have 6 factorial over, and if you remember, 2 factorial is just a 2, so I'm just going to write a 2, times the 4 factorial. Now expand the 6 until you get to a 4. So you have 6 times 5 times 4 factorial. Those 4 factorials will cancel, so I have 6 times 5 over 2, which is 15. 6 times 5 is 30, and then divided by 2 is 15. Well, let's look at how to do combinations on the calculator. Remember, the permutations were above the number 9. Combinations are above the number 8. It's the NCR. So if I want the number of combinations of 8, choose 3. I'm going to type in my 8, hit second and then the number 8 to get to the combination, and then type in a 3 and hit equals. And that gave me the 56 we got by working the formula out by hand. In the second example, it was the number of combinations of 6, choose 2. So type in a 6, hit second number 8 for the combination, and then type a 2. And that gives me the 15 that we got by hand. Now let's look at some word problems using combinations. If Jeff must read 5 books from a reading list of 10 books, how many ways can these 5 books be chosen? If Jeff is reading 5 books, I don't know the order he reads the books in. It doesn't say anything about which book he has to read first or second or third. So in this example, order does not matter. In fact, if he just tells me the books that he read, I will not know what order he read them in. So this is a combination. My N is a 10 because I have 10 books to choose from, and my R is a 5 because I'm selecting 5 of those 10 books to read. So using the calculator, I type in a 10, I hit second 8 to get to the combination, and then I type in a 5 for the 5 books I'm reading. And this gives me 252. So there are 252 ways Jeff could select the books to read. In the next example, how many ways can a group of 5 people be chosen to leave class early if the class size is 40? So the first thing you have to do is decide, is order important? If I'm selecting 5 people to leave class early, there was no importance placed on which person I select first or second or third. Basically, those 5 people I select are going to get up at the same time and leave class. So there's no advantage to being selected first over 5th. So in this example, order does not matter. So it's a combination. I have 40 students to choose from, and I'm choosing 5. So it's a combination of 40 choose 5. So on the calculator, I type in a 40, I hit second 8 to activate the combination, and then the 5 that I'm selecting. So I end up with 658,008. So there are 658,008 different ways the students could be chosen to leave early. In the next example, you have a bowl of 12 marbles. How many ways can you draw 8 marbles out of the bowl? So in this example, there's no importance placed on the order I choose those 8 marbles. I'm just going to reach in and grab 8 marbles. It doesn't say anything about the first marble being more important than the 8th marble. So if the problem doesn't place any importance on the order, order doesn't matter. This is a combination of 12, choose 8. So on the calculator, I type in a 12, second 8 for the combination, and then 8 because I'm choosing 8 marbles. So this gives me 495. So there are 495 ways the marbles can be drawn. In the next example, a class has 13 women and 8 men. How many ways can a group of 4 women and 3 men be formed? This example is a little bit different because I have to separate the women and the men. Don't group those together. So of the 13 women, I'm choosing 4 for the group. Of the 8 men, I'm choosing 3 for the group. The problem didn't tell me anything about the order being important, so it doesn't matter if you were selected first or second or third. So these are both combinations. For the women, I have 13, choose 4. For the men, I have 8, choose 3. These are 2 separate actions, so I'm going to apply my fundamental principle of multiplication, and I'm going to multiply these 2. So on your calculator, if you do 13, choose 4, you're going to get 715. If you do 8, choose 3, you're going to get 56. And then multiply these, and you end up with 40,040. So there are 40,040 ways the group can be formed. Next, you have a bowl of 10 red marbles and 12 blue marbles. How many ways can you draw 8 marbles, of which 5 are red and 3 are blue? So again, in this example, I'm going to keep the colors separated. So I'm going to consider the red marbles and the blue marbles. Of the 10 red marbles, I'm selecting 5. So it's a combination of 10, choose 5. Of the 12 blue marbles, I'm selecting 3. So it's a combination of 12, choose 3. And I used combinations because the problem didn't tell me anything about the order being important. These actions are independent, so I'm going to multiply them. If I use my calculator, the combination of 10, choose 5 is 252. The combination of 12, choose 3 is 220. If I multiply these, I get 55,440. So there are 55,440 ways the marbles can be drawn. Now let's look at some mixed examples from the past couple of lessons. First, how many different words can you form using the letters of the word Tennessee? I'm rearranging these letters, so order is important. So this is a permutation. It's a permutation with the repeated letters, so I have to remember to divide by the factorial of the number of times the letters are repeated. So let's look at the letters in the word Tennessee. There's 1 T, there's 4 E's, there's 2 N's, and 2 S's. So I'm going to take the 9 total letters, and it's a permutation of 9, choose 9. But I have to divide by 4 factorial times 2 factorial times 2 factorial. And that's for the 4 E's, the 2 N's, and the 2 S's. We'll do the numerator and the denominator separately in your calculator. A permutation of 9, choose 9 gives me 362,880. Then in my calculator, if I type in 4 factorial, then do times 2 times 2, because remember 2 factorial is just 2, you're going to get 96. If you divide this, you get 3,780. So the letters in the word Tennessee can be arranged 3,780 different ways. Look at this next example. Using Scrabble tiles, where you have one T, two N's, two S's, and four E's, how many ways can I spell Tennessee? This time I'm not arranging the letters in the word Tennessee. I'm wanting to use those letters and actually spell out the word Tennessee in that order. So it's still a permutation, but there's several restrictions. When there's a lot of restrictions, I'm going to use the method I did in the previous lesson of drawing the blanks. This time I specifically want to spell out the word Tennessee. So I want that first blank to be a T. Well, I only have one Scrabble tile that's a T, so I only have one to choose from. For the next position, I want it to be an E. Well, I have four E's to choose from, so I have four options. My next position needs to be an N. I have two Scrabble tiles that are N's, so I have two to choose from. My fourth position is another N. Well, I began with two N's, but I've already used one in the third position, so I only have one left to choose from. Next, I come to another E. I started out with four E's, but I've used one of them, so I only have three left to choose from. Next, I have two S's. For the first S, I have two childs to choose from. And for the second S, since I've used one of the S's, I only have one left to choose from. Now I come to my final two E's. I began with four E's, but I've used two of them, so that means I have two left for the third E. And for the final E, I only have one tile left. Now if I multiply these, I end up with 96. So using those Scrabble tiles, I could spell Tennessee 96 different ways. For the next example, you draw a single marble from a jar that contains 15 red marbles, 10 blue marbles, and 5 white marbles. How many ways can you draw a red or a blue marble? This example is a single action event. Since I see the word or, I'm going to apply the addition counting principle. My single action is drawing that one marble, and I'm asked for the possibility of two events, drawing a red or drawing a blue. So I find the number of ways to do each of these events, and I'm going to add them. So I'm going to add the number of red marbles to the number of blue marbles. Since there's 15 red marbles, I have 15 ways to draw a red marble. Since there are 10 blue marbles, I have 10 ways to draw a blue marble. So I have 25 ways to draw a red or a blue marble. Next, how many 5-digit numbers can be formed using the digits 1, 2, 3, 4, and 5? And the leftmost digit must be odd, all digits must be used, and no digit can be used twice. This example is a permutation because order matters. When I'm arranging objects, if I write these numbers as 1, 2, 3, 4, 5, that's one order. If I write it as 3, 2, 4, 5, 1, that's a different order. But this time I have several restrictions. The left digit has to be odd, all digits have to be used, no digit can be used twice. When I have a lot of restrictions, I revert back to drawing the blanks. It's a 5-digit number, so I'm going to draw 5 blanks. Well, if you remember, the first digit had to be odd. I have 3 odd numbers to choose from, the 1, the 3, and the 5, so I have 3 choices. For my remaining digits, I can use any of the numbers. I just can't repeat any numbers. So I started out with 5 numbers, but I put one of the odd numbers first. So that leaves me with 4 numbers to choose from for the second digit. Now I've used 2 of the 5 numbers, so I have 3 left to choose from for the third position. Now I've used 3 of the 5 numbers, so I have 2 left to choose from for the next position. And finally, since I've used 4 of the 5 numbers, I only have 1 left to choose from the last position. I apply the multiplication principle and multiply these, and I get 72, so that means 72 different numbers could be formed. The next example, how many other 4-digit numbers have the same digits as 6449, 6,449? This again is a permutation because the order matters. If I write it as 4649, that's a different order than 4469. And I also have to keep in mind I have repeated letters, or this time repeated numbers. I have 2 4s. So I'm going to have to divide by the factorial of those. I wasn't given a lot of restrictions, so I'm going to write this as a permutation of 4 choose 4. There are 4 digits, and I'm using all 4 of them. But as we mentioned before, we have 2 4s, so I'm going to divide by 2 factorial. Well, if I type into my calculator permutation of 4 choose 4, remember the permutation is above the number 9. I end up with 24. 2 factorial is a 2. So I have 24 divided by 2, which is 12. But be really careful. I found that there's 12 different ways to arrange the digits in the number 6449. Look at what you were asked for. You were asked for how many other 4-digit numbers. So of those 12, I don't want to include the 6449. That's one of the 12. The 12 was my total. I'm asked for the other numbers. There are 11 other numbers that could be formed. Pay really close attention to the wording on these problems. Next, if you must answer 3 out of 5 discussion questions on a test, how many ways can you select 3 to answer? I have to decide if order matters or not. If you're taking a test from me and there were 3 discussion questions, I don't know the order you answered those questions in. I don't know if you answered the first one first, the second one second, and the third one third. You could have answered the last question first. So since I don't know the order you answered these in, order does not matter. It's going to be a combination. I have 5 questions to choose from, and I'm choosing 3 of them. So it's a combination of 5 choose 3. If you do this on your calculator, you get 10. So there are 10 ways to choose the questions to answer. In the next example, you draw a single marble from a jar that contains 15 red marbles, 10 blue marbles, and 5 white marbles. How many ways can you draw a blue or a white marble? This is similar to another example. We have a single action experiment, and we're asked for an OR. I want to find the number of ways to draw a blue or a white. So I'm going to use the addition counting principle. So I take the number of blue marbles and I'm going to add it to the number of white marbles. There were 10 blue and 5 white, so there's 15 ways to draw a blue or a white marble. Next, you have your choice of 3 different English classes, 5 different algebra classes, and 2 different history classes. How many ways can you select one of each class to take? and assume there are no scheduling conflicts. So if you're selecting your schedule for next semester, and you have to take an English class, an algebra class, and a history class, you're going to choose one of the 3 English classes, one of the 5 algebra classes, and one of the 2 history classes. This we're going to use our multiplication principle. There's several independent actions. So we're going to take the 3, the 5, and the 2, the 3 for the English, the 5 for the algebra, and the 2 for the history, and we're going to multiply those. We end up getting 30, so there are 30 ways to select the classes. Next, how many different ways can 7 people stand side by side? In this example, order matters, so it's a permutation. It's basically a lineup. If I put person 1 first and person 2 second, that would give me one lineup. If I switch those two, that's a completely different lineup. It's a different way to arrange the people. So I can work this with a permutation of 7 people, and I'm choosing all 7. If you type this into your calculator, you get 5,040. If you remember from a previous lesson, I did a lineup by drawing the blanks. You could also work the problem this way. This is a problem where you have the option of using the permutation or drawing the blanks. If I have 7 people to choose from, for the first position, I have 7 options. I have 7 people. After I place one person in line, I have 6 left to choose from for the second position. After I place 2 people in line, I have 5 people for the third position. And I continue on. For each position, I have 1 less person. So I have 4, and then 3, and then 2, and then 1. If I multiply these, I get the same 5,040. So there are 5,040 different ways for the people to line up. If there's not a lot of restrictions given, I use the permutation. If I have a lot of restrictions, I wouldn't use the permutation. I would definitely draw the blanks. Next, you draw a card from a standard deck of cards. How many ways can you draw a black card or a heart? Well, this is a single action. I'm drawing one card, and I'm considering the possibility of 2 events, a black card or a heart. So I'm going to use the addition counting principle. I find the number of ways to draw a black card, and I add that to the number of ways to draw a heart. In a deck of cards, there are 26 black cards, and there are 13 hearts. If I add these, I get 39. So there's 39 ways to draw a black card or a heart. In the next example, if you coach a co-ed basketball team that has 7 male athletes and 6 female athletes, how many ways could you select 2 males and 2 females to put on the court at one time? Now, if you think about a basketball team, if I'm selecting 3 of the 7 men, the order I select them does not matter. They go out on the court all at the same time. Since the order doesn't matter, it's a combination, but I do have 2 separate actions. I'm going to keep my men and my women separate since I have to have 3 men and 2 women out on the court. So of the 7 men, I'm going to choose 3. And of the 6 women, I'm going to choose 2. I multiply these. So in your calculator, if you do 7 choose 3, you get 35. If you do 6 choose 2, you get 15. 35 times 15 gives me 525. So there are 525 ways to choose the players. Next, if you have 20 people in a class, how many ways can you select a president, vice president, and a secretary for that class? So this time, out of 20 people, I'm choosing 3, but the order I choose those in have an importance. Since I'm giving the 3 people chosen a specific title, order is important. So it's a permutation. So it's a permutation of 20 choose 3. If I type that into my calculator, I get 6,840. Now I could also look at this problem drawing the blanks. We'll say the first position represents the president. Well, when selecting a president, I have 20 people to choose from. After I select one person to be president, I need to select my vice president. Well, of the 20 people in class, I can't choose the president to be vice president, so I only have 19 choices remaining. Now I've chose a president and a vice president, I need to choose a secretary. Of the 20 people, 2 have already been selected, so I have 18 remaining. If I multiply these, I also get the 6,840. So there are 6,840 ways to select those 3 officers. Now you draw a card from a deck of cards. How many ways can you draw a 5 or a face card? Again, this is a single action. I have 2 events, draw 5 or a face card, so I'm going to use my addition counting principle. So I take the number of 5s and add that to the number of face cards. There are 4 5s in a deck, and there are 12 face cards in a deck. So if I add these, I get that there are 16 ways to draw a 5 or a face card.